Good evening everyone, good evening. I welcome you all again to the NEET Elite. Hope you guys are doing great, having the good time. Well people, if I'm audible and visible to everyone, let me know in the chat box with the thumbs ups. Let me know in the chat box with the thumbs ups if I'm audible and visible to every single guy right here. Let me know. Good evening everyone, welcome to the session. Welcome to the session. Welcome guys, welcome. So well, as you all must be knowing, today it's going to be the part 2 of thermodynamics, and people, in the today's session what we are going to do is we are going to talk about the first law of thermodynamics. We'll be talking about the enthalpy function, reversible and irreversible processes, isobaric, isochoric, isothermal and adiabatic processes, and at the end we'll be talking about the entropy and the Gibbs free energy of the reaction. Yes. So before starting the session, let me introduce myself. As you all must be knowing now, my name is Wassim Sir and I'm your chemistry master teacher right here. Yes. Alright, so people, before starting the session, let's get to know about the Vedantu NEET Pro subscription, like what all benefits you guys are going to get if you'll enroll yourself in this Pro subscription. If you are getting this Pro subscription, what all benefits you guys are going to get. Let me tell you, in this Pro subscription, you guys are going to get 5,000 plus hours of live online teaching. Regular tests and assignments will be provided to you, which contains more than 10,000 questions. There are 20 plus teachers with 5 plus years of experience who will be training you personally for the upcoming NEET 2021 as well as 2022. And people, at the same time, you have got the option to learn either in English or in Hindi. It's completely your wish to select the language, get trained by the master teachers of Vedantu right here, okay? And at the end, we are going to cover everything which includes your micro as well as crash course over here through this Pro subscription. Yes? Okay, so talking about the NEET 2022, talking about for the ones who are going to write the NEET in 2022, let me tell you, we have come up with 4 different plans, as you all can see. On every plan right here, we have got 20% off. 1 month plan, 3 month plan, 6 month plan and 12 month plan after the 20% off is available for 4K, 10.8K, 19.2K and 33.6K respectively. Yes? Okay. So for the ones who are the droppers, yes, for them we have come up with 3 different plans, as you all can see right here, right on your screen. 1 month plan, 3 month plan and 6 month plan after the 20% off. You guys are just getting it for 7.2K, 20.4K and 40.8K respectively, okay? And all these plans are valid for the NEET droppers over here, okay? So people, how to get these plans? Let me tell you, there is a link in the description box of the video. I want you guys to click on the link, use the coupon code as WSPRO. On using this coupon code of WSPRO, you guys are going to get 20% off in whatever plan you're selecting for yourself. Yes? So do get enrolled in this if you want to get benefited for the upcoming NEET 2021 or 2022. Yes? Okay, so people, let me know in the chat box if you guys are ready, if you guys are super duper excited for the session. Let me know in the chat box with the thumbs ups. Let me know in the chat box with the thumbs ups if you guys are super excited for the today's session. Yes. Yashwant has come up with a quote, you're more beautiful than the light of sunset. As you look at the beautiful sun forgets all your stress and greet your evening with a big smile. Good evening to all my lovely sir. Thank you, bro. Thank you so much. Thank you so much. Thank you. Let me know if you are super duper excited for this session. It's going to be a long session, guys. Let me tell you that, okay? That's wonderful. People are super excited about it. That's great. Okay. So let's get started with something called as first law of thermodynamics. Okay, we are starting from the first law of thermodynamics. Okay. Have a look, guys. First of all, let me tell you, this first law of thermodynamics, it is basically the energy conservation principle. It's an energy conservation principle, you can say, okay? And as per the first law of thermodynamics, when the state of the system changes, there is a change in the internal energy of the system. Yes, and that change in the internal energy of the system is brought about in 2 ways. Number 1, when heat is absorbed or released by the system. Number 2, when work is done by the system or on the system. What is meant by that? How can we get it mathematically right here? See guys, first thing, the first law of thermodynamics, it's definitely the energy conservation principle, number one. And as per the first law of thermodynamics, whenever the state of the system changes, there will be a change in the value of internal energy for the system. Yeah? Whenever the state of the system changes, internal energy of the system automatically changes. And that change in the internal energy can be brought about in two ways. Number one, when heat is absorbed or released by the system. Number two, when work is done by the system or on the system. Okay? Before talking about the first law of thermodynamics, if you remember in the last session of thermodynamics, I told you whenever heat is absorbed by the system, Q value is taken to be positive. Whenever heat is released by the system, Q value is taken to be negative. Yeah? And whenever work is done by the system, W value is taken to be negative. Whenever work is done on the system, W value is taken to be positive. All these things we have covered in the last session, if you remember. So whenever heat is absorbed by the system, Q value positive. Whenever heat is released by the system, Q value negative. Whenever work is done by the system, W value negative. Whenever work is done on the system, W value is taken to be positive. Yeah? Now guys, let's get it mathematically right here. See, for example, I'm taking a container in which I have got an ideal gas, for example. Okay, let's say I've got a container. In this container, I have got the ideal gas. So the ideal gas present in this container right here is my system. Okay, let's assume the internal energy of this ideal gas is equal to U1. U1 is the total energy present in the system. U1 is what I call as internal energy of the system right now. Okay, for example, I'm supplying some Q amount of heat. Let's say I'm supplying some Q amount of heat to the system. Or I can say system is absorbing the Q amount of heat right here. And when the system would have absorbed Q amount of heat over here, can I say the total energy, the total internal energy of the system now is going to be U1 plus Q. Yeah, because the system has absorbed Q amount of heat right here. Okay. Now I'm assuming I'm doing some work on the system. Work is done on the system. Yeah, I'm doing some work on the system. And whatever work is done on the system, that work is again stored in the system in the form of its internal energy. So can I say now the internal energy of the system will become U1 plus Q plus W, because work is done on the system, and whenever work is done on the system, W value is taken to be positive. Okay, can I say this is going to be the value of final internal energy of the system, which I'm representing by U2. U2 is the final internal energy of the system, which is basically equal to U1 plus Q plus W. Yeah. Now, as we all must be knowing, internal energy is a state function. If internal energy is a state function, can we calculate its absolute value? We cannot calculate the absolute value of a state function. Yeah. We always calculate change in the value of state function. Correct? We always calculate change in the value of state function. Now, we will have a look what I'll be doing right here. When the system has reached this state, which is the final state right here, at that time, the total internal energy of the system, which I'm representing by U2, is equal to U1 plus Q plus W. Okay, so take this U1 on this side, it's going to be U2 minus U1, or instead of U2 or minus U1, I'm going to write delta U. Delta U means change in internal energy, which is simply going to be equal to final internal energy of the system minus internal energy minus initial internal energy of the system. It's going to be equal to Q plus W. This is the mathematical formulation of first law of thermodynamics right here. And people, you need to be careful with the terminologies. That's it. You need to be careful with the sign conventions and the terminologies. Remember, whenever heat is absorbed by the system, Q value will be taken as positive. Whenever heat is released by the system, Q value will be taken as negative. Whenever work is done on the system, W value is taken to be positive. Whenever work is done by the system, W value is taken to be negative. You just have to be careful with the sign conventions right here. Okay. Now let's get to know how this concept, how this mathematical formulation of first law of thermodynamics is used in the questions. Okay. Right. Now we will see. Have a look. Before doing the questions, you should know the relation between different units of pressure, volume, and the values of R, right? Remember guys, different units of pressure. ATM is the unit of pressure, Newton per meter square is the unit of pressure, millimeter of Hg is one more unit of pressure, torr is one more, bar is one more. You should remember the relation between the units of pressure right here. Remember, 1 ATM is equal to 1.01325 into 10 power 5 Newton per meter square, or we call it as Pascal, which also equals 760 mm of Hg, which also equals 760 torr, which is equal to 1.013 bars. Yeah. Similarly, talking about the units of volume, I'll be in need of these units frequently while doing the questions. Yeah, units of volume. Remember, 1 decimeter cube is equal to 1 liter, which is equal to 1000 centimeter cube, which is equal to 1000 ml, which is equal to 1000 cc, and cc stands for cubic capacity. Yeah, right? And people at the same time, the values of universal gas constant. The first value of the universal gas constant R is going to be 8.314 joules per Kelvin per mole. Second one is going to be 0.0821 atm liter per Kelvin per mole, and the third one is going to be 1.98, or approximately you can take it as 2 calories per Kelvin per mole. And people, in the questions, if I need to use this value, I am not going to use this value as 0.0821. Instead of 0.0821, I'll be using 1 by 12 in order to reduce the calculations, okay? 1 by 12 is exactly equal to 0.0821 only, okay? Now let's get to know how these units are used in the questions and how first law of thermodynamics questions are asked to you in your NEET examination. This is the very first and the basic question as per the first law of thermodynamics is concerned. Have a look. See guys, as per this question, a system expands from 5 liters to 10 liters. That means this is the case of expansion. This is the case of expansion. Initial volume of the system is given as 5 liters. Final volume of the system, which I'm representing by V2, it's given as 10 liters. Yeah. A system expands from 5 liters to 10 liters against a constant external pressure of 2 atm. I'm given with the external pressure value as 2 atm. Yeah. This is something which I'm given with. Well, if in doing so, the system absorbs 800 joules of heat. That means while this expansion is happening, the system is absorbing heat. How much heat it's absorbing? It's absorbing 800 joules of heat. Yeah. So Q value, I'll be taking it as, should I be taking it as plus 800 or minus 800? Heat is absorbed by the system, and whenever heat is absorbed by the system, the value of Q is taken as positive. So it's going to be plus 800 joules. What are we supposed to calculate? We are supposed to calculate the value of delta U. Very, very simple, correct? Yes. Now people, as per your first law of thermodynamics, we know delta U किसके बराबर होता है? Delta U is equal to Q plus W. Yeah. Correct? Now people, I'm going to write it like this. Delta U is equal. What is the value of Q? Do I know the value of Q? Absolutely, it's plus 800 joules. And I'm going to write its units with it so that you won't get confused or something. Yeah. Now, delta U is equal to plus 800 plus W. Plus W. What is W? W is simply minus P external or V2 minus V1. W is simply minus P external V2 minus V1. Minus P external delta V, right? Yes. So people, can I get the value of W from here, from this equation? It's going to be minus times. What is the value of P external? P external is 2 atm. V2 minus V1. Final volume of the system is 10 liters. Initial volume is 5 liters. Can I say I'll get the value of W from here as it's going to be minus 10. And what are the units of this W? Since I have taken pressure in atm and volume in liters, so W value is going to be atm liter right here. W is going to be atm liter right here. Yeah, minus 10 atm liter right here. Okay. Right? Now we will have a look. If W is equal to minus 10 atm liter right here, remember first of all, 1 atm liter is always equal to 101.3 joules. 1 atm liter is always equal to 101.3 joules. And at the same time, remember, 1 bar liter is also equal to 100 joules. These are two important things which you need to know right here, okay? If W is equal to minus 10 atm liter, if I want to convert it into joules, it's going to be minus 10 multiplied by. We know 1 atm liter is equal to 101.3 joules. Yes, so it's going to be minus 1013 joules right here. I got the value of W in joules. Now I'm going to put the value of W into this equation. I'll be done with the equation, yeah? It's going to be plus. What is the value of W which I got? I got the value of W as minus 1013 joules right here. Yeah. So people, can I calculate the value of delta U from here? It's going to be simply 800 minus 1013. 800 minus 1013 is the value going to come as minus 213 joules right here. Okay. So I got the value of delta U which I was supposed to calculate in joules. Yeah. Let me know in the chat box if it is clear to everyone right here. Let me know in the chat box. Let me know in the chat box. Yes. Wonderful, guys. This is something which we were supposed to calculate. Yeah. Hi, Sanjay. How are you doing? Let's move on to one more question, guys. Let's move on to one more question. You can easily solve this question as well. For the system undergoing the process in which delta U is given as 300 joules and system absorbs 400 joules of heat undergoing expansion against 0.5 bars. Calculate the change in volume delta V in liters. You can easily calculate this one by simply putting putting all the values into the first law of thermodynamics equation, yeah? You are given with the delta U, you are given with the external pressure, you just have to calculate the value of delta V, yeah? Correct? Yes, you can simply do it and you will be letting me know the answer of this question in the comment box afterwards, yeah? It's a very simple question. Okay, now let's get to know something called as enthalpy function. Enthalpy function, okay? Enthalpy is first of all represented by H. It is represented by H, okay? First of all, talking about the enthalpy function, let me first of all tell you what was the need to give the enthalpy function, okay? Why the concept of enthalpy function was introduced. Have a look, guys, understand. Let me write it over here somewhere. See, as per the first law of thermodynamics, we know delta U is equal to Q plus W. Yes, as per the first law of thermodynamics. What is delta U? Delta U is nothing. It is simply final internal energy of the system minus initial internal energy of the system. Yes. So isn't it going to be U2 minus U1? U2 minus U1 is equal to Q plus W. W is simply minus P delta V. W is simply minus P delta V, right? So I'm going to write Q minus P delta V. Delta V means final volume of the system minus initial volume of the system, yeah? Now people, if I'll write the same equation keeping the pressure of the system constant, when the pressure of the system will be kept constant, and then I'm going to write this equation. It's going to be U2 minus U1 is equal to, instead of Q, I'll be writing QP. What is QP? QP means heat exchanged between the system and the surroundings at constant pressure. Heat exchanged between system and surroundings at constant pressure. Yeah, it's going to be QP minus P V2 minus V1. Yeah, this is something which I got, correct? Now people, if I'll just shuffle this equation a bit, it's going to be U2 plus PV2 minus U1 plus PV1 is going to be equal to QP. I have taken all these terms into this side and then I have shuffled them a bit, yeah? Now people, over here, understand one important thing. I got a new function right here, U plus PV. U plus PV. U plus PV basically I'm calling as the internal energy. Sorry, enthalpy. Enthalpy function is nothing. It is just the sum of internal energy and pressure volume work. Enthalpy is nothing. It is just equal U plus PV. This U plus PV is what I call as enthalpy. The sum of internal energy and the pressure volume work of the system is what I call as enthalpy function. Yeah? Correct? Now we will see. Let's say I've got the system. Let's say I've got the system right here. Correct? Let's say I've got the container in which I've got the gas. And the system right here is kept at constant pressure. The system is kept at constant pressure. The pressure of the gas right here in the container is fixed, it's constant, yeah? Let's assume the internal energy of this system right here is equal to U1. Let's say the volume occupied by this system right here is V1. Let's say pressure of this system is P, okay? At this time, let's assume its enthalpy is equal to H1, okay? Now people, I'm just changing the state of the system. After changing the state of the system, keeping the pressure constant, let's assume the final internal energy of the system is U2. The final volume of the system is V2. Pressure of the gas still is equal to P. And when the internal energy of the system is U2, volume of the system is V2, pressure of the system is P, let's assume at this time the enthalpy is represented by H2, yeah? H2 is the final value of enthalpy, H1 was the initial value of enthalpy right here, correct? Now people, understand. If I'll write this equation for the initial state, can I write it as H, instead of H, I'll be writing H1 is equal to U1 plus PV1. This is the equation which I've written for the system, which was kept at initial state. What about the final state? For final state, H2 is going to be U2 plus PV2, yeah? So instead of U2 plus PV2, should I be writing H2? Instead of U1 plus PV1, should I be writing H1? Absolutely. So what I'll be getting right here, I'll be getting one important equation. Instead of U plus PV2, I'll be writing H2. Instead of U1 plus PV1, I'll be writing H1 is equal to QP. Now people, H2 minus H1, final enthalpy minus initial enthalpy of the system. I'm going to represent it by delta H. So delta H value I got to know equal to QP. So people, from this equation, can I define the change in the enthalpy? Yes. Yes. What is delta H? Delta H is the change in the enthalpy of the system. Can I say change in the enthalpy of the system is actually equal to heat exchanged between the system and the surroundings at constant pressure? Yes. So I can simply define change in the enthalpy of the system is always equal to heat exchanged between system and surroundings at constant pressure. Okay, remember this is very important. Okay, and people, remember at the same time, in the last session in which we talked about the internal energy, I gave you one important result, that was QV, and QV used to be equal to delta U. Right? QV used to be equal to delta U. What was QV there in the internal energy? QV was heat exchanged between system and surroundings at constant volume. It is equal to change in internal energy. Yeah. So remember, whenever in a question you are supposed to calculate the heat exchanged between system and surroundings at constant pressure, that actually means you are supposed to calculate the value of delta H for the system. And whenever you need to calculate the value of QV, whenever you need to calculate the value of heat exchanged between system and surroundings at constant volume, remember at that time actually you are supposed to calculate the value of delta U, which represents change in internal energy. This is very important, which you must be knowing before doing the enthalpy questions right here. Yeah. Now we will have a look on what I'll be doing now. Let me tell you about this enthalpy. Enthalpy is a state function. It's a state function. And people, can we calculate the absolute value of a state function? No. We always calculate change in the value of state function. Yeah, we always calculate change in the value of state function. And that change in the value of enthalpy is represented by delta H, which is going to be equal to final enthalpy of the system minus initial enthalpy of the system. Yeah, remember it at the same time. And people, enthalpy, it is an extensive property. It's an extensive property. The value of enthalpy of a system changes on changing the amount of substance present in the system. Yeah. What is extensive property? How do we define the extensive property? As you all must be knowing, extensive property is the one whose value changes on changing the size of the system, on changing the amount of substance present in the system. If I change the amount of substance present in the system, the value of enthalpy of the system will automatically get changed. So enthalpy is your extensive property right here. And at the same time, remember, enthalpy depends on pressure and temperature. Enthalpy is the function of pressure and temperature. On changing the pressure, on changing the temperature of the system, the value of enthalpy automatically gets changed. Yes? Okay. Now people, let's get to know a few more important things about this enthalpy function right here. Okay. Before talking about few more important things about enthalpy function, let me tell you few important results right here. Okay. Let me tell you few important results right here. Okay. Remember guys, small change in the value of enthalpy for 1 mole of ideal gas. Small change in the value of enthalpy for 1 mole of ideal gas is always equal to Cp dt. Is always equal to Cp dt. What is Cp? Cp is the molar heat capacity at constant pressure. Yes. Correct. Small change in the value of enthalpy. Small change in the value of enthalpy for 1 mole of ideal gas is always equal to Cp dt. This relation is valid for 1 mole of ideal gas. I've chosen my system as ideal gas and I've taken its 1 mole. Yeah. Similarly, if I'll be having n moles of ideal gas, small change in the value of enthalpy for n moles of ideal gas is always going to be n Cp dt. Okay. This is valid for n moles of ideal gas. I hope you remember this. I've taught this in detail. Yeah. Okay. Now people, if dH is the small change in the enthalpy for n moles of ideal gas, can I calculate the total change in enthalpy? Yes. And how do I calculate total change in enthalpy? I just need to integrate this. On both the sides. Yeah. Just integrate it on both the sides. Correct. Now people, right here, I'm integrating with respect to temperature. Let's say temperature of the system is changing from T1 to T2. Let's say I'm changing the temperature of n moles of ideal gas from T1 to T2 and I'm supposed to check what is the total change in enthalpy. For example, I've got n moles of ideal gas in the container and I'm changing the temperature of n moles of ideal gas from T1 to T2. I need to calculate change in enthalpy. Change in enthalpy is going to be simply equal to delta H, which represents the total change in enthalpy. It's going to be equal to number of moles of the gas, constant, I'll take it out. If Cp is independent of temperature, If Cp does not depend on temperature, I'll take the Cp again out. Integral of dt is T. Yes, give the limits, upper limit, lower limit, it comes as a T2 minus T1. So people, you got one more important result right here. Delta H is nothing, it is NCP delta T for n moles of ideal gas whose temperature changes from T1 to T2, yeah? Yes, this is the value of change in the enthalpy for n moles of ideal gas whose temperature changes from T1 to T2. I want you guys to take a note of it. This is very, very important, yeah? This is very, very important. And in the last session of internal energy, I gave you similar equation like this. I told you delta U is equal to NCV delta T for n moles of ideal gas whose temperature changes from T1 to T2. If I'll be having n moles of ideal gas in the container, if its temperature is changing from T1 to T2, the change in the value of internal energy is going to be NCV delta T. The change in the value of enthalpy is going to be NCP delta T, right? And both these equations are valid for the ideal gases right here, okay? Yes? Now guys, one more important thing about this enthalpy. See, let's say I've got an isothermal process. What is an isothermal process? That process in which temperature of the system is kept fixed, temperature of the system is kept constant. Yeah, we know that. Yes, if temperature of the system is kept constant, can I say delta T, change in temperature, is going to be 0 for the system? Yeah. If delta T is 0, we know delta H is equal to NCP delta T. NCP delta T. Let's say I've got the system which contains the ideal gas. Let's say the ideal gas is my system, yeah? If the temperature of the ideal gas is kept constant, I'll say delta T for the ideal gas will be 0. If delta T is 0, I'll simply say delta H will be 0, right? This is valid for what? For the ideal gas which will be undergoing the isothermal process. Yes, the ideal gas which will be undergoing the isothermal process, for that ideal gas, the value of delta H will be always equal to 0. Yes. Now people, based on the sign of delta H, we classify processes into two, yeah? Number one is called as endothermic process. Number two is called as exothermic process. Based on the sign of delta H, we classify the process into two types, endothermic and exothermic, right? Endothermic process is the one in which the value of delta H for the process will be, delta H for the system will be positive. Exothermic process is the one in which delta H for the system comes out to be negative. Yes, based on the sign of delta H, we classify the process into two types. One is called as exothermic, one is called as endothermic. For endothermic processes, the value of delta H for the system will be coming out to be positive. For exothermic processes, the value of delta H for the system will be coming as negative, yeah? Now people, if the delta H for any system which will be undergoing any process, if it comes out to be positive, I can simply say NCPT2 minus T1, this value will be coming as positive. When can this value come out to be positive? When the difference of these two terms will be positive. When will be the difference of these two terms positive? When T2 will be greater than T1. What is T2? T2 is the final temperature of the system. T1 is the initial temperature of the system. So can I say for any system whose delta H will be coming out to be positive, the temperature of that system will be increasing with time, yeah? Because T2 is the final temperature of the system whose value comes out to be greater than T1, initial temperature, right? So for any system whose delta H value comes out to be positive, we say temperature of that system increases with time, yeah? Similarly, for any system which will be undergoing exothermic process, for any system whose delta H will be negative, what does that mean? That means NCPT2 minus T1 will be coming as negative. When can be this term negative? When the difference of these two terms will be negative. When can be difference of these two terms negative? When T1 will be greater than T2, where T1 is the initial temperature of the system, T2 is the final temperature of the system. Can I say for any process whose delta H value will be coming out to be negative, I'll say temperature of the system will be decreasing with time. Yes, remember this at the same time, yeah? These were some basic things which you need to know about it, yeah? Philip, T means temperature of the system right here, yeah? Temperature of the system will be decreasing with time. Temperature of the system will be increasing with time right here in the endothermic process. And in the exothermic process, temperature of the system will be decreasing, yeah? Got it? Okay. I mentioned it over here. For any process whose delta H value will be negative, we call that process exothermic, in which the temperature of the system will be decreasing with time. And at the same time, for endothermic processes, For endothermic processes, delta H value will be positive. If delta H is positive, I'll say temperature of the system increases with time. Okay? This is something which you all must be knowing. This is one basic question which I want you guys to take a note of and let me know its answer in the chat box. Yeah? For 1 mole of ideal gas, a curve between enthalpy and temperature. I've plotted a curve for 1 mole of ideal gas between enthalpy and temperature. And the curve is like this, yeah? Now, people, I have marked 2 points on this curve, A and B. Now, I need to check at which point A or B Cp value will be more. How do I get to know that? At which point Cp value is going to be more? What do you think? What do you think at which point Cp value will be more? Let me know in the chat box. Let me know in the chat box. It's a simple thing, guys. Few minutes back, I told you small change in the value of enthalpy for 1 mole of ideal gas is equal to Cp dt. Yes. Can I say Cp from here is equal to d upon dt of H? Correct? What is this dH upon dt? Can I say dH upon dt gives me the slope of this curve at any point? Yeah. What is dH upon dt? It gives me the slope of enthalpy versus temperature curve. Yes. So can I say more the value of slope at a point, more will be the value of Cp, less the value of slope, less is going to be the value of Cp. Very, very, very simple. Correct? Now, I need to check at A and B. Where will be the slope more? Wherever slope is going to be more, there only Cp value is going to be more. Correct? Now, the point is, how do I get to know about the slopes? See, guys, first thing, I'll be drawing one tangent right here. I've drawn one tangent. Let's assume the tangent is making the angle theta A with the positive x-axis in the anti-clockwise direction. Now, similarly, I've drawn one more tangent right here. And let's assume this tangent is making angle theta B with the positive x-axis in the anti-clockwise direction. Can I simply say theta A is greater than theta B on just looking at the angles? Can I say theta is greater than theta B? If theta A is greater than theta B, can I say tan of theta A will be greater than tan of theta B? Yes. If tan of theta A is greater than tan of theta B, I can simply say slope at A, which I'm representing by M. Slope at A is greater than slope at B. And wherever slope is going to be more, there only Cp value is going to be more. Can I say Cp value at point A will be simply greater than Cp value at point B? Let me know in the chat box if it is clear to you. Cp value at point A is greater than Cp value at point B, which I just calculated, which I just checked by just comparing the slopes at 2 points. Yeah. Let me know in the chat box if it is clear to everyone. Correct? Let me know in the chat box. Let me know in the chat box so that I can move on to few more things, few more important things right here. Yes? Okay. Let's move on. Let's move on. And let's talk about the relation between delta H and delta U. Okay? Relation between delta H and delta U. Understand what I'll say. We know, guys, few minutes back, I told you enthalpy is nothing. It is a function which is basically U plus PV. U plus PV is what we call as enthalpy. Yes. If I'll multiply this equation throughout by D, if I'll differentiate it basically, dH will be equal to du plus d of PV. Yes, I'm differentiating this equation throughout. I'm multiplying this equation by D throughout. Yes. Now, if I'll integrate this, can I say integral of dH is going to give me delta H? Can I say integral of du will give me delta U? Can I say integral of d of PV is going to give me delta of PV? This is one general equation which I want you guys to remember, and this is actually the relation between delta H and delta U for any process. Yeah. Now, people, let's say I've got the condition. I'm specifying a condition. Let's assume the pressure of the system is constant. Let's assume the pressure of the system is constant. If pressure of the system is constant, can I say at that time delta H will be equal to delta U? I'll take the pressure out, so it's going to be P delta V. This is the relation which I'll be using when pressure of the system will be constant. Similarly, if I assume volume of the system to be constant, can I say at that time delta H will be equal to delta U plus I'll take V out of it. It's going to be V and it's going to be delta P. This is the relation which I'll be using when the volume of the system will be kept constant. Yeah. Now, people, if both pressure as well as volume of the system will be changing, if both pressure and volume will be changing. If both pressure and volume are changing. At that time, which equation I'll be using? I'll be writing delta H is equal to delta U plus, I'll be writing something like this, P2V2 minus P1V1. This is the equation which I'll use when the pressure as well as volume of the system change with time. Yes? These are the three equations which you need to remember. Basically, you're not going to remember these three equations. You just need to remember one master equation. From this, you can conclude anything. Yeah? Now, people, if I'll be having a homogeneous gaseous phase reaction, let's say I've got a homogeneous gaseous phase reaction. Homogeneous gaseous phase reaction carried out at constant temperature. Carried out at constant temperature. For example, the reaction is like this. N1A gas, it gives N2B gas. Yes, let's say this is one homogeneous gaseous phase reaction which is carried out at constant temperature. Okay. Now, people, first thing, if I want you guys to calculate the value of delta Ng for the reaction, can you do that? Can I say delta Ng for the reaction is going to be simply number of moles of gaseous products, which is N2, minus number of moles of gaseous reactants, which is N1. Now, what is going to be the relation between delta H and delta U for the homogeneous gaseous phase reaction? It's going to be delta H is equal to delta U plus. It used to be delta of PV, yeah, but instead of PV, now I'll be using nRT, yeah. I'll be using delta of nRT, correct? Now, this reaction is taking place at constant temperature. I'll take the temperature out. R value is already constant. I'll take the R value out. So, I'll get one equation like this. Delta H is equal to delta U plus, this is going to be delta of Ng multiplied by R multiplied by T. This R reactants, which is N1. These are few relations which you need to remember and apply in the equations. Now, the point is how to apply these relations in the equations, yeah? Understand how to apply these relations in the equations. The first question, guys, which is on our screen, you can easily solve this one. You can easily solve this one. Have a look. Calculate delta U when 2 moles of liquid water vaporizes at 100 degrees centigrade. The heat of vaporization of water, that means delta H value is given to me as 40.66, yeah? 40.66 kilojoules per mole. I'm supposed to calculate the value of delta U, okay? How will I be solving this sort of equation? Understand. First of all, this is going to be H2O liquid and I'm vaporizing it to H2O gas. I'm vaporizing it to H2O gas. Yes? People, is this a balanced chemical equation? Yes, this is a balanced chemical equation. For this balanced chemical equation, what is the value of delta H which is given to us? Delta H is given us as 40.66 kilojoules per mole. Yeah? This is something which is given to me. What am I supposed to calculate? I'm supposed to calculate the value of delta U. Is that? Now, first thing, I'm going to calculate the value of delta Ng for the reaction. Delta Ng for the reaction is going to be equal number of moles of gaseous products, which is 1, minus number of moles of gaseous reactants. Over here, it is in liquid form, so 0. Delta Ng value I got as 1 for this balanced chemical equation right here, correct? Now, people, if delta Ng is 1, can I use the formula, simple formula between delta H and delta U? We know delta H is equal to delta U plus delta NGRT, correct? Now, what is the value of delta H which is given to me? I'm given with the value of delta H as 40.66 kilojoules per mole is equal. I need to calculate the value of delta U in kilojoules as well, correct? Plus delta Ng. Delta Ng value I got as 1. R value I'll be using as 8.314 joules per Kelvin per mole. Joules per Kelvin per mole. Temperature is given to me as 100 degrees centigrade. That means 373 Kelvin. Correct? Now see, guys, understand. Over here I've got the value of delta Ng. This is the value of R. This is the value of temperature. If I ask you what is going to be the unit of this whole term, unit of this whole term is going to come in joules. Unit of this whole term is going to come in joules. So if I'll divide it by 1000, now I'm going to get the unit in kilojoules right here. Correct? Yes, because I've taken this in kilojoules, so this should be also be in kilojoules right here. When you'll calculate the value of delta U from here, you'll be getting the value of delta U as 37.5 kilojoules. This is the value of delta U which you'll be getting by solving this, okay? So should this be the answer? Should this be the answer? What do you think? Should the value of delta U for the reaction be 37.5 kilojoules? No way. Why is that? Have a look. This is the value of delta U. This is the value of delta U for the 1 mole of, for the vaporization of 1 mole of liquid water. This is the value of delta U for the vaporization of 1 mole of liquid water. But do I have only 1 mole of liquid water? I have 2 moles. I have 2 moles of liquid water. So for the vaporization of 1 mole of liquid water, delta U value is 37.5. So for the vaporization of 2 moles of liquid water, delta U is going to be 37.5 multiplied by 2. Value is going to be how much? Value is going to be 75 kilojoules. So for the vaporization of 2 moles of liquid water, the value of delta U will be coming out to be 75.1 kilojoules right here. And the option 2 is going to be the correct one among all, yeah? Yes? Is it clear to everyone? Let me know in the chat box so that I can move on and give you a lot of other questions as well. Let me know in the chat box. Yes? Okay. Okay, Said, we'll be talking about that at the end, okay? Let's move on to one more question. Let me see if you can solve this one or not. Again, a very simple question. 1 mole of ideal gas undergoes a change in state, okay? 2 atm 3 liter to 2 atm 7 liters. With the change in the internal energy, delta U is equal to 30 atm liter. The change in enthalpy for the process in atm liter will be. What do you think should be the answer? Let me know in the chat box. What do you think should be the answer? Let me know in the chat box. What do you think should be the answer? Is that? Let's see how to solve this question. I've got 1 mole of internal energy which undergoes a change in state. When 1 mole of ideal gas was present at the initial state, its pressure was 2 atm. And its volume was 3 liters. Okay? And when this ideal gas has undergone a change in the state, now its pressure is again 2 atm, but its volume is 7 liters. Yes, this is the initial state of the gas, this is the final state of the gas. Okay, now we will have a look. When the state of the system has changed, has the value of pressure of the system changed, or pressure is remaining constant? Pressure has remained constant. Yes. So people, if the pressure is constant, pressure during this process is remaining constant. So I can use the equation delta H is equal delta U plus, this is going to be P delta V, that means V2 minus V1. Yes, this is going to be the equation which I'll be using right here. Correct? What am I supposed to calculate? I'm supposed to calculate the value of delta H. Can I say delta H is simply going to be equal to delta U. Delta U is given to me as 30 atm liter plus P value, pressure is 2 atm, V2 minus V1, final volume minus initial volume, 7 minus 3. So isn't it going to be 38 atm liter? So 38 atm liter is going to be the value of delta H which we were supposed to calculate, right? Yes. Let me know in the chat box if it's clear. Yes? Wonderful, guys. Let's move on to one more question. Let me see if you can solve this one or not. See, again a very, very simple question. I'm given with the reaction carbon monoxide gas plus 3 times H2 gas, it gives CH4 gas plus H2O gas, okay? Which of the following is correct for the following exothermic reaction? It is mentioned in the question that the reaction is exothermic. If the reaction is exothermic, that means heat will be released by the system. And whenever heat is released by the system, Q value is taken to be negative. Q value is taken to be negative. Correct? But over here, one of the options says Q value is greater than 0. But we know the process is exothermic, so Q value must be negative. So this cannot be correct. This is wrong. This is wrong. Correct? Now, what about the relation? What about these three things? What about these three things? This is more than one option correct, I guess. Let's check it out. Let's check it out. If I ask you, is the reaction balanced or not? Absolutely, the reaction is balanced. Can I calculate the value of delta Ng for the reaction? I can do that. It's going to be number of moles of gaseous products, which is 1 plus 1, that is 2, minus number of moles of gaseous reactants, which is 1 plus 3, that is 4. So 2 minus 4 is simply minus 2. I got the value of delta Ng. Yeah. People, if I got the value of delta Ng, can I use the relation delta H is equal to delta U plus delta Ng RT? I can use this relation. Absolutely. Now guys, delta H will be equal to delta U. What is the value of delta Ng? That is minus 2 multiplied by R multiplied by T. Now check this equation, guys. Let me know, is delta H more or delta U more? Can I say from this equation delta U is greater than delta H? Yes. Yes, I can say that. Delta U, from this equation I can easily say delta U is greater than delta H. Correct? So delta U is greater than delta H. So just check the option number second. So option number second is correct. Yeah. Now, so this will be automatically the incorrect one. Now what about this one? What about this one? The following exothermic reaction is carried out at constant pressure. At constant pressure. And it is the exothermic reaction. That means pressure and temperature of the system is constant. Yes. And at constant pressure and temperature, can I say volume of the gas is directly proportional to moles of the gas? Right? Can I say more the value of N, more the value of V, less the value of N, less the value of V? Yeah, I can say that. Now we will have a look. On the reactant side, how many moles of gas we have in total? 3 plus 1, 4 moles. On the product side, how many moles of gas we have? 1 plus 1, 2 moles. When the reaction is happening, when the reaction is proceeding in the forward direction, are the moles of the gases increasing or decreasing? Moles of the gas are decreasing. If moles of the gas are decreasing, can I say volume will be also decreasing? Yes. Decrease in the volume is what we call as compression. Correct? 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 Decrease in the volume is what we call as compression. And whenever there is compression, work is done on the system. And whenever work is done on the system, W value is taken to be positive. But over here it's mentioned W value is negative. So this cannot be the answer. Yeah. Let me know in the chat box if it is clear. Let me know in the chat box if it is clear to everyone. Yeah, since number of moles are decreasing when the reaction takes place, when the reaction moves in the forward direction, number of moles of the gas are decreasing. That means volume will be decreasing. Decrease in volume is what we call as compression. And whenever there is compression, work is on the system and W value is taken to be positive. Yeah. Correct? Okay. Let's move on to a few more. Let me see if we can solve these or not. The value of delta U is found out to be this much. For this at this, calculate delta H for the reaction at the same temperature. Can you do this, guys? It's very simple. It's very simple one. You can do this one, yeah? You can easily solve this one. You just have to use the relation delta H is equal to delta U plus delta Ng RT. Correct? So first of all, if I need to calculate the value of delta Ng for the reaction, it's going to be number of moles of gaseous product, which is 1 plus 1 is 2. This is a liquid state. I've got nothing to do with this. So 1 plus 1 is 2 minus number of moles of gaseous reactants. It's going to be 3 divided by 2. It's going to be 3 divided by 2. Over here is in solid form. I've got nothing to do with this. So it's going to be simply 2 to the 4. 4 minus 3 is 1 divided by 2. So I got the value of delta Ng for the reaction. Yes, I got the value of delta Ng. Okay. Now people, what am I supposed to calculate? I'm supposed to calculate the value of delta H. Do we know the relation? Delta H is equal to delta U plus delta Ng RT. Yes, this is one reaction which I took. Okay. We are supposed to calculate the value of delta H and I'll be calculating it in kilojoules. Okay. It's going to be equal to delta U. Delta U value is given to me as minus 742.7 kilojoules per mole. So it's going to be minus 742.7 kilojoules per mole. Yes. Plus delta Ng. Delta Ng value I got to know as 1 by 2. Correct? R value I'll be using as 8.314. Temperature is given to me as how much? Temperature of the reaction is given to me as 298 Kelvin. Now people, one important thing, if I ask you what is going to be the units of this whole term, it's going to be joules. So I'll divide this by 1000. Now it's going to be in kilojoules. You just need to solve this equation. You'll be getting the value of delta H from here. Yes. And that delta H will be coming in kilojoules per mole. Yeah. Let me know in the chat box if it's clear to everyone again. Yes. Again, a very, very simple question this was, guys. Okay. Let's move on to one more question which is on your screen. For the combustion of C6H5COH at 300 Kelvin and 1 atm pressure, heat released is 300 kilojoules. Calculate the heat released at constant volume for the combustion of this process. Yeah. See, again, a very simple question. How to solve this sort of equation? See, first of all, What is mentioned? For the combustion of this at 300 Kelvin and 1 atm. Pressure is constant. Pressure is given as constant, 1 atm. And heat is released. Heat is released at that means heat is getting released at constant pressure. Heat is being released at constant pressure. And heat released at constant pressure is represented by QP. Heat released, heat exchange between system and surroundings at constant pressure. If heat is being released, I'll write it as minus 300 kilojoules. Yes, minus signifies that the heat is getting released. Yeah. Correct? Number one. What are we supposed to calculate? Heat released at constant volume. We know heat exchange between system and surroundings at constant volume is actually equal delta U. Correct? And QP is actually equal delta H. If you remember, I told you in the beginning, heat exchange between system and surroundings at constant pressure is actually delta H. Heat exchange between system and surroundings at constant volume is actually delta U. Do I know the relation between delta H and delta U? I need to calculate the value of QV, heat exchange between system and surroundings at constant volume. That actually means I need to have the value of delta U. Whatever is going to be the value of delta U, same is going to be the value of QV. Yeah? Very, very, very simple. Okay? So people, you know the relation. Delta H is equal to delta U plus delta NGRT. Yes. Delta H value, that means QP value, it's given to me as minus 300 kilojoules is equal. Delta U we are supposed to calculate plus delta Ng. Delta Ng for the reaction, what it's going to be? It's going to be 7 minus 15 by 2. That will be minus 1 by 2. Yeah. Minus 1 by 2 is the value of delta Ng. R value you'll be taking as 8.314 joules per Kelvin per mole, and temperature is given to us as how much? 300 Kelvin. Now people, if I ask you what are going to be the units of this whole term, units of this whole term will be in joules, so I'll be dividing it by 1000 so that it gets converted to kilojoules. Now this is the equation in front of you. You just have to calculate the value of delta U, and whatever value of delta U you'll be getting, that is going to be the answer in kilojoules. Yeah, and that is going to be the heat exchanged, heat released at constant volume. Yeah. So Shaista is saying the answer is coming as minus 298.7. Okay, the value of delta U by solving this equation is coming as minus 298.7 kilojoules right here. Yeah, this is going to be the value of delta U, which is actually going to be the value of QV. Okay, right? Yes. Okay, let's move on. Let's move on to something called as reversible and irreversible processes. First of all, let me know in the chat box if is everything clear till here or not. Let me know in the chat box with a thumbs up if everything is clear till here or not. Let me know in the chat box. Yeah? Okay, that's great. Now let's talk about something called as reversible and irreversible processes. Okay, first thing, few points I want you guys to get note of right here. Reversible, these are very slow processes, and irreversible, these are very fast processes. Okay, second thing, in reversible processes, driving force is greater than the opposing force only by a small amount, whereas in case of irreversible processes, driving force is far greater than the opposing force. Yeah, and at the same time, reversible processes are imaginary processes, whereas irreversible processes are real processes. Now, how can we get this concept right here? How can we get this concept right here? It's very simple, guys. See, for example, I need to lift this marker up. Let's say I'm lifting this marker up. Okay, if I want to lift this marker up, how many forces are being experienced by this marker? The first force which I'm giving in upward direction, the second force, gravity, is pulling it towards itself. So there are two forces acting on this marker when I'm lifting this marker up. Yeah, the force which I'm giving by means of which it is going upwards, that's called as driving force, and the force which the gravity is opposing its motion, that's what I'll be calling as the opposing force. Yeah, now if I'm lifting this marker up fastly, can I say driving force is far greater than opposing force? Yeah. So in irreversible processes, which are actually the fast processes, in those processes driving force is far greater than the opposing force. That's why this marker was going up fastly. Yeah, correct. Now people, one more thing. Now there is one more scenario. I'm lifting this marker slowly. There are two forces experienced by this marker, driving force as well as opposing force. Driving force is the one which I'm giving to the marker by means of which the marker is going up in the upward direction. Opposing force is this way, yeah? Correct? Now people, the marker is slowly going up. That means driving force is greater than the opposing force only by a small amount. That's why marker is going up slowly, yeah? Very simple. Correct? Which I have already mentioned right here in case of reversible processes, driving force is greater than the opposing force only by a small amount, yeah? And if driving force is far greater than the opposing force, the marker will be going up fastly. If driving force is greater than the opposing force only by a small amount, marker will be going up slowly, yeah? Marker will be going up slowly, correct? Now, let's get to know this reversible and irreversible processes right here in detail, okay? Let's talk about this reversible and irreversible processes and let's relate it to our thermodynamics right here. See, let's say I'm going to show you the case of expansion. Expansion of ideal gas, okay? See guys, let's say this is the container right here, and this is the piston of the container. And over here you have got the ideal gas. Let's say the piston right here is at point A. And when the piston is at point A, let's say volume occupied by the gas is V1. When the piston is at point A, volume occupied by the gas is simply V1, okay? Now I need to show you the case of expansion, yes? Now piston has to move from point A till point B. Okay? Now there are two ways by which piston can move. Either the piston will be going out fastly or the piston will be going out slowly. If the piston goes out fastly, I'll be calling the process as irreversible process. If the piston will be going out slowly, I'll be calling this expansion as reversible expansion. Yes? There are two ways by which expansion can happen right here. One is slow expansion, which is going to be the reversible expansion. Another one is fast expansion, which is going to be the irreversible expansion. Yeah? Correct? Now we will understand one important thing. See, can I say on this piston, two pressures will be acting. This is going to be the pressure of gas in this direction. This is going to be the external pressure. Can I say if P gas is far greater than P external, at that time piston will be suddenly going out, yeah? What is P gas? Can I say P gas right here is the driving force and P external is the opposing force, yeah? P gas is the driving force by means of which piston goes out and P external is the opposing force, okay? If P gas is far greater than the P external, can I say at that time the process is going to be fast, it's going to be irreversible, yeah? And we already know in irreversible processes, driving force is far greater than the opposing force, yeah? Correct? Now this piston can slowly go out as well. If the piston is slowly going out, that means definitely pressure of gas is greater than the external pressure only by a small amount. That's why piston is going slowly out, yeah? This is the case of reversible expansion. This is the case of irreversible expansion. Yes? Let me know in the chat box if it is clear to everyone. Yes? Let me know in the chat box if it is clear to everyone. This is the case of reversible expansion. This is the case of irreversible expansion. In reversible expansion, P gas and P external. No doubt P gas is greater than P external only by a small amount, or I can say P gas is almost equal to P external. Yeah? P gas is almost equal to P external. Now we will see one important thing. How do I calculate work? There are two ways by means of which I can calculate work. Okay, one will be valid for reversible process, one will be valid for irreversible process. See, the general expression to calculate work is minus integral from initial volume to final volume. It is going to be P external multiplied by dV. Yes. For reversible processes, P external is almost equal to P gas. So I can write it like this. W is equal to minus integral from V1 to V2. Instead of P external, I'll be writing P gas, pressure of the gas, multiplied by dV. This is the formula by means of which I will be calculating the work done in case of reversible process, in case of slow process. Yes. Now what about irreversible process? What about irreversible process? In irreversible process, which I saw right here, external pressure is being constant. Yes, external pressure is being constant. Say, if external pressure is being constant, I can calculate work right here as minus P external integral of dV. Integral of dV is what? That is V. Take the limits, V2 minus V1. It's going to be delta V. Yes, so I got the W value, work done. How do we calculate work done in irreversible process? It is simply going to be minus P external delta V. These are two things which you need to remember. This is how we calculate work done in reversible process. This is how we calculate work done in irreversible process. Yes, this is something which we have talked about in detail when I taught you actually the reversible and irreversible processes. Yes, this was just a quick overview of it. Okay. Now we will one more important thing. What is that? Have a look. See. If I'll be having a PV curve like this, let's say this is pressure.